Yes, I'm trying to grab this nanoparticle out. I really wanted to show it to the people for the video. Well, I got tweezers. Well, how small can a nanoparticle be? That small, eh? Well, yeah, how big my well, I got maybe 1 or 2 millimeters at the tip, I guess. I don't know. I might as well be trying to pick up a penny using a backhoe. Okay, I guess I'll keep trying to grab this nanoparticle. I really want to show it to the guys in the video. I mean, it's all about nanoparticles and microparticles. I need to focus something else. All right, thanks for your help. This has been great. Thank you. Well, it seems tweezers are out when it comes to being able to pick up nanoparticles. Who knew they were so small? You may be wondering, why are we talking about particles? I thought this was a polymer video. Well, one of the issues with polymers is we often talk about them being used for drug delivery or medicinal delivery. For these kinds of applications, you don't usually use the solid polymer as a whole. That is occasionally used in implant and coating deliveries, but typically the polymer has to be reconfigured and reformed into some kind of a system that can be applied into the human body and is small enough not to cause trouble. As you may be well aware, human body doesn't particularly like having things that are non-self inside of it. It tends to react badly. So one of the ways to deal with this, of course, is to take your polymer material and to make it into these tiny little microparticles or nanoparticles. Now, for the purpose of this video, we will define microparticles as anything that is within the micron range. That is scaled between 1 millimeter down to 1 micrometer. Typically, though, injectable microparticles, which are used for clinical formulations, they usually range on the small end of that scale. Usually, they're well below 200 micrometers and typically down to that 1 micrometer or slightly above type size range. That's what's usually used. The key element for a microparticle in terms of its sizing is its application, because microparticles are an injected material. They have to be small enough to fit through a syringe needle and not plug, not cause any trouble in that case. Microparticles, however, do not need to be small enough to move in the bloodstream. In fact, they're designed to not move in the bloodstream. They're intended for use as a intramuscular or subcutaneous injection. So essentially they're injected into a part of the body where the particle itself is not going to move around. It's going to be trapped inside of a given area, and they'll stay there and slowly release drug over a long period of time. More on that later. So what does a microparticle look like? Well, I happen to have some right here. In the dry state, it's kind of like a powdery little stuff here. They do have a tendency to clump typically upon storage, so usually some kind of an anti-caking agent or some other material like that, just to keep them from sticking to each other, is usually applied to make sure they disperse out. When they get in the liquid state, I don't know how well it shows up on the video there, but you can actually see microparticles. The micron scale is visible to the human eye. It looks like dust, but it is visible. You can generally see that they're there. Nanoparticles are a much smaller material to work with. So when you look at a solution of nanoparticles, it essentially looks more or less like milk. There's not a whole lot to see. Since we're dealing with scale, nanoparticles are usually designed to flow, since they are ones that are scaled below 1 micron in size. So you're dealing with anything from 1,000 nanometers down to 100 so nanometers or so. Once you get below that kind of size range, you're dealing with not quite the atomic scale of molecules and such, but you're getting close. There are many processes for making microparticles. Obviously, one of them is not simply cutting it down to micron size with a knife, although that would be fun. That's not typically the way they are generated. Most common is the emulsion technique for generating microparticles. This technique is done by essentially taking an aqueous solution, usually of a surfactant, polyvinyl alcohol for example, or some other material, which can create a micelle. We covered micelles in a prior video. Taking the solution, that surfactant, mixing it in with water, and stirring it overhead. while it's stirring to create this emulsion, you add in the polymer and medicine dissolved in an organic solvent. As it's swirling around inside this emulsion, the polymer and the organic solvent will naturally form into the middle of the micelle regions, and they'll create microparticles as they harden inside of there. Now, this process can be used to make microparticles, usually with a pretty high concentration polymer and organic solvent, relatively low stir speed. Same process can be used to make nanoparticles. Typically, you just have to boost your stir speed a little bit with something like this, a high-speed homogenizer. Now keep in mind, this is not necessarily specific to nanoparticles, but it's usually what's the type of item used for making that. This is essentially designed to stir a solution at an extremely high rate, thousands and thousands of RPM. This allows you to create essentially very, very small micelle regions, and then that allows you to control more precisely how size the particles are, or at least shrink them down. Now I will specify for an emulsion type methodology, the word control is kind of a loose one. This methodology is based off a lot of random chance. How does the polymer get into the micelle? How does it precipitate out away from the water phase, which it does not dissolve in? All these things are kind of random. There's similar methodologies that have been developed recently using microfluidics, which essentially performs this kind of action. However, it performs it inside of tiny little channels where the water and the organic solvent are mixed together at very well-known rates, very well-known amounts. And in this mechanism, the nanoparticles and microparticles have a very uniform size applied to them and have very uniform properties. So that's what's used typically for making those. There are other methodologies as well for making nanoparticles. There's thin film nanoparticles, there's dialysis methodologies for making nanoparticles, but they all essentially have the same concept in common, is that you're taking your polymer and you're relying on the fact that it doesn't like water. And you're using the fact that it does not like water in order to make the polymer collapse in on itself into these tiny little spheres and beads. Now, what do these look like? Well, let's see a picture of one. Over these past several videos, I've used many visual aids in order to explain various aspects of polymer properties and their mechanisms. I'm trying to think of a good one to use for microparticles and nanoparticles. As you know, I've used the little emoji guy, and we've done plenty of fun time with chains, and you all remember even this thing. But I just need something that's a little bit more explanatory of what a microparticle and a nanoparticle work like, and what they look like, and how they behave. It's one of those cases where they're just particles, they're just smaller. So I need something that's just like something else, but just smaller. I know, children. They're like people, they're just smaller.
Microparticle. I stay still, but I live for a long time.
I explained, once they are injected, microparticles don't move around. They generally stay where they've been injected. They're effectively trapped. At such a large size, they're too large to fit through capillary tubes or other blood vessels. And that's by design. They're not intended to go into the bloodstream themselves. What they are intended to do, however, is to stay where they're put and then slowly start to release the medicine. Now, microparticles last for quite some time. There are clinical formulations and medicines that are available on the market now, which are designed for anywhere from weeks to up to 6 months of delivery of an active medicine molecule from the microparticle. Now, how do you have such wide diversity in times? This actually plays into how does the medicine come out of the microparticle. That's related both to how fast does the medicine diffuse through the microparticle, as well as what is the microparticle's degradation. As you remember previously, the PLGA microparticles, and microparticles made of polyesters that biodegrade, they will, over the course of time, start to break down. The chains become smaller, pores open up. The medicine has new ways to leak out of the microparticle as degradation occurs. And during this time period, they're continuously releasing more and more and more medicine out into the bloodstream. Ideally, they are releasing medicine in the bloodstream about the same speed at which it is being cleared out of the bloodstream by the liver and kidneys and other processes within the human body designed to clean out the bloodstream. So this is where we talk about having microparticles that have a certain rate of release. It's not simply that they release fast or they release slow, it's that they release the right amounts at the right speed in order to maintain efficacy. So there has to be enough medicine in the bloodstream in order to make sure that the effect of the medicine is enough that the patient feels better, but not too much that there are some side effects caused by having too much medicine in the bloodstream. This is why microparticle formulations are a little bit tricky. It's not just simply mixing the PLGA with some medicine and then tossing it in. The medicine has to be able to distribute appropriately inside the PLGA so it's not all stuck to the outside, for example, of the microparticle. The medicine also has to have at least some affinity for the PLGA, typically for long-term type of applications, so that the medicine doesn't just simply elute out right away. As well as, of course, the PLGA properties have to be determined in order to know what kind of speed are they going to degrade at. Ultimately, the best way to find out how to make a microparticle formulation is to simply manufacture some and then test it to see what kind of release rates it has. And there's many tests that are being developed and have been developed in order to determine this. The tests that we have for in vitro assays, essentially, which is taking the microparticle and then mixing with either a saline solution or a certain surfactant solution, which is designed to more or less mimic human conditions, they're not perfect. Ideally, we're trying to develop tests that have a good in vitro, in vivo correlation, which is to say that the test release rate matches that observed in vivo in actual usage. Usually these are not exactly the same. Even with that, however, in vitro tests will still give you useful information about the microparticle release rate. At the very least, it'll tell you whether it releases right away or if it releases incredibly slowly. And then you will have something to work off of from there. That's essentially how microparticles are designed to work. They have been used for many different formulations. Typically they come into play for either a formulation that requires a daily injection, which, as you can imagine, most patients do not want to be injected daily, or for formulations in which patient compliance is an issue, where the patient may not desire to go in for having the injection repeatedly. So these are where these are typically used.
I'm fast!
Nanoparticles, on the other hand, are designed to move. They are small enough that they can flow through the bloodstream without causing any clotting or any other issues. They are designed to fit quite nicely through any area, since the average blood cell, you're talking 5 to 10 micrometers in size. Nanoparticles, being less than 1 micrometer in size, are substantially smaller than that of a human cell. This allows them to flow not only through bloodstream, they can enter into human cells quite easily. Because of this, nanoparticles have the capability to deliver things to cells themselves, such as a DNA or RNA type delivery for gene therapy type applications, which is a really novel and unique kind of usage for these types of material. Often you're dealing with molecules which are either poorly water soluble or are rapidly cleared out of the bloodstream, and the order of magnitude of even minutes sometimes. In this situation, there is an advantage to encapsulating that particular medicinal molecule inside of a nanoparticle so that it can last longer in the bloodstream. This most notably affected is when you apply a nanoparticle which has polyethylene glycol on the outside. A polyethylene glycol is a material, it's a water-soluble polymer that does not elicit an immune response. One of the nice features behind it is, in fact, it resists immune response, such that it prevents the drug and the nanoparticle itself from being cleared out of the bloodstream for a longer period of time than had it not been there. Nanoparticles can be modified so that the exterior surface of them has a specific group or a decoration on the exterior of the shell. If this decoration or group is, for example, an antibody or a ligand or something else, then you can have it so that the nanoparticle is essentially sticky. This is where we will talk about something in biochemistry called ligand protein binding. So within biochemistry, it is common to have proteins and certain markers and other factors which can fit together. This is a ligand and a protein that conjugate well, and they attach to each other and they'll hold. This is actually a conformation they prefer. Other conformations using some other protein, of course, they don't fit, they don't work, it doesn't want to stay there, has no attraction to it. A powerful methodology here is attaching the ligand on the outside of a nanoparticle, which matches that of a cell, which is either a disease state or has some property that you want to deliver to that cell. Often, this is applied if you can find a ligand which conjugates specifically to cancer cells. Then you can create a nanoparticle which is specific. It will effectively bind to and attach to cancer cells because of the ligands which cover its exterior surface. I got it. Oh, I dropped it. Well, I hope you learned something today about microparticles and nanoparticles. In truth, we are just beginning as a species to scratch the surface of the capabilities of these amazing compounds and formulations which can be created simply by making something very, very small.